Question 14. We are considering, right, the true weight of an object, right, at the equator versus at the pole. So here, right, the assumption is Earth is rotating about the pole, and Earth is a uniform sphere. So we are removing, right, all complications and just comparing, right, pole position with equator. So what is the true weight? How does they compare? Well, true weight, right, is simply Fg. Okay, no complication about this. So this simply, right, equals to you can think of it as mg, or you can just write out the m over r square. So you see, right, that at equator and at pole, if Earth is a uniform sphere, there's no difference between the r, no difference between the capital M, so on. So, right, we must have the same true weight. Okay, no complication. Now, what is different is, right, the idea of apparent weight. Okay, apparent weight. So suppose, right, you drop this. Okay, drop this object, right, at the pole. You have a particular g. Okay, and you drop this, right, at the equator. You will have another g. Okay, which one will be larger? Answer is, right, at the pole will be larger, because, right, at the pole mg, right, is equals to g1. Okay, this g is a apparent g. Okay, so turns out, right, at the pole the apparent gravitational acceleration, right, is equals to the real g. Okay, so forgot the m. Yeah, so this net force equals to ma equation. Okay, what about at the equator? At the equator, right, you have F net equals to MA. Okay, but you see here, maybe I shouldn't call it G. Let me just change my notation. I think it'll be better if I just call it A. Okay, so A of free fall. Okay, is A of free fall as well. But you note that they are talking about different acceleration of free fall. Okay, so on the Earth equator, right, we have mg equals to m2a here. Okay, the total a, right, is equals to g, which is the around 9.81. But, right, it has to give rise to two effects, which is, right, centripetal acceleration, okay, and acceleration due to free fall. This centripetal acceleration is really small. You can figure it out, right, by r omega square. Okay, r is radius of Earth, so 6.4 times 10 to the power of 6 times 2 pi over Earth's rotation, 1 day, 64, 86, 400 second. Okay, putting square. Okay, with this, right, you can figure out that this AC, right, is around 0.03 meter per second square. So suppose, right, this guy is 9.81, then this guy, right, will be around 9.78 meter per second square. So at the poles, right, you have a larger free fall acceleration. At the equator, right, part of the 9.81 need to make the object, right, go in circular motion together with Earth. Okay, so that the object, right, don't feel like it's lagging behind. Yeah, because it's already in circular motion. Whether, right, you say that this object, right, is at rest before you drop the object, right, doesn't matter, because, right, when you say the object is at rest, right, before you drop it, it means that it's already spinning, right, with Earth rotation. That's why, right, when you observe it, it appears to be at rest above ground. Yeah, That mean, because Earth is the ground is really rotating with rotating as part of Earth rotation, right? If you observe something to be at rest, it means right it is also performing circular motion. So this thing right is present as long as the object is on the equator. Yeah. So if a question right is asking for what's the acceleration of free fall, then you got to realize right at equator is smaller than at the pole.